Well, I was going to minimize it to show you how to find enthalpy values besides the ones in your book. So this would be something you can learn to do for your own benefit. You know, if you have a reaction in the future that you want to know if it works, or if you have a homework assignment where the value is not listed in the textbook. So you don't want to just Google enthalpy of gasoline, let's say, because what's going to happen is you're going to get non-standard conditions, and a lot of websites don't tell you whether it was 1 mole or at 25 degrees or what the pressure was. So what we want to do is be very, very selective about where we get our data from. It turns out there is an entire government organization that does nothing but collect reliable data in one place for thermodynamics. And they also control how we measure stuff, right? So this government agency is called the National Institute for Standards and Technology. So NIST hosts the WebBook. Okay, and so just Google NIST WebBook, and it will take you to this website. And we can search by a variety of means here. I'm just going to use the formula that we're looking at. And so in this case, it's C8H18. I happen to know, this is organic chemistry, so I wouldn't expect you guys to know this. I would give you the name. I happen to know that that's octane, so we're going to choose octane. Okay. And what we're looking for is the thermochemical data. So there's a couple different choices, gas phase or condensed phase. So if I had C8H18 as a gas, I would pick this one. But we have a liquid, so that's a condensed phase. Solids are also condensed, okay? And so we have all these different values. These are entropies, so we're not going to use those this semester, but we are going to use enthalpies. And we have a couple different values here, but they're pretty consistent, okay? So I would choose to use the 250.3 because we have 2 data points here that kind of support it. I also choose it because there's references to support it. And so another choice would be this one, but there's no references for it. So that makes me suspicious that maybe that's not as reliable. So this 250 has 2 different data points, 2 different references, both properly cited. So I'm going to use that value in my calculation. Okay. And I know it's standard conditions because the F in the degree symbol are there. So that's what I want to use. All right, so we're going to go back to our PowerPoint here. Okay, so here's where we left off. We've looked up the value for octane, so that's going to be 250 kilojoules per mole. Right, so I just make a nice list of all my delta H of formations here. So here's my list. And I like to do it just underneath the chemical reaction because that way I can keep straight what's what. And then for oxygen in our appendix C, elements are always 0 enthalpy, so that's pretty easy. And then under carbon dioxide here, that's going to be under the carbon listing. It is negative 393.5 kilojoules per mole. And water, again, water is weird because they put it under oxygen. We said this was probably hot, so it's going to make a gas, not a liquid. And so I'm going to pick H2O gas, which is negative 241.82. Okay. So now that I've defined all of the values that I'm going to use in my Hess's law calculation, now I'll use it, right? So Hess's law says that the delta H of our reaction is the sum of all your products. So we're going to take all the products and add those together first, and then subtract the sum of all the reactants. Okay. So when you do this, I highly recommend getting in a very good habit of clearly defining your delta H's first, because if you pull these incorrectly, your answer will be wrong. The only way I can give you partial credit is if I can figure out where you messed up. So the more you show me, the better off you will be. Don't cut corners. Also, cutting corners has a habit of making things be wrong. So our products are 16 of these CO2s. So we're going to first go, I'm going to make this a bracket. So 16 times the enthalpy for each one, plus, so that's sum, right? Plus the enthalpy of 18 waters. Okay, Now these calculations can get kind of long, so this is the one and only place where I don't require you to put units in the calculation so long as you have defined them properly above. Okay, so there's our products, and then I'm going to make another bracket for the reactants. So my reactants here are 2 there, plus 25 oxygens, which is 0. Okay, so I did some math for us, and so this simplifies to just 2 terms. Oops, except I messed this up. Hang on. So here, this is actually 500 kilojoules per mole, because 2 times 250. Okay, so in the last step, I'm going to take this and add, watch your signs. Do you see that? So I forgot to put my negative, but it's really important that you do. So I'm going to add these 2 negative numbers, which is going to give me something like negative 10,500, 10,600, something like that. And then subtract this, and we're going to find out that the delta H is quite big. So here we end up with a negative number minus another negative number, and so we get an even more negative number. So out of this value, we get negative 11,149 kilojoules per mole of octane, of gasoline. That's a lot. That is a lot of energy. So that's an extremely exothermic reaction, which is exactly what you would expect, because we would never use something as a fuel that was endothermic, because energy would have to go into it, and we're looking to get energy from it. So we use octane as a fuel because it's really, really good at it. Produces a lot of energy. Okay, so that's our Hess's law problem, and we're going to have a lot of those. That's one of the main ideas in this chapter. The next one is the idea of calorimetry. So in our simulation in class, we looked at some calorimetry. We took a brick and we put it into some hot water. And even when the brick was really, really cold, it didn't absorb all that much heat. That's because bricks are insulators. Okay, so calorimetry is connected to enthalpy, but it's also about how heat transfers. There's 2 different kinds of calorimetry. So the first one is called bomb calorimetry, and this one's kind of cool because, you know, it sounds awesome. This is what we call constant volume calorimetry. So in other words, we have a constant volume of water. It's not changing. Nothing, you know, nothing is allowed to leave the bomb. It's a sealed system. And so what it is we have this little chamber where our actual system is going to be put in there, and we have electrodes going into it. So this is commonly used to determine how many calories are in food, for example. So I put my little sample of food in here. I know exactly how much is in there so that at the end I can divide by the mass or the moles. And I connect my electrodes in there. And those are what's going to combust the food. When they do, the heat released from the reaction goes into the surrounding environment, which is this canister. And then the canister is in direct contact with water, which is being stirred because I want to make sure not to have like a hot spot over here. I want to make sure to have an even homogeneous water sample to measure. And then what we actually record is the change in temperature of the water. And we use water because it's very stable and has the ability to absorb quite a lot of heat. And so we can calculate based on the temperature change of the water how much heat was generated by the food. And that's how we get calories. Okay, so this is constant volume. Constant pressure is what we use to figure out delta H, because we defined delta H value equal to heat at constant pressure. This is a bit simpler, a little bit less finicky. So we have 2 coffee cups, which are an excellent insulator. So they are attempting to make an isolated system. So neither matter nor energy leaves the system. And we have a thermometer and a mixing thing. So in our case, actually, we have a glass. We don't use glass thermometers for this experiment any longer. We use metal probes. So your metal probe actually works pretty well as a stirrer as well. And again, we need to stir it to make sure it's homogeneous. And what we're measuring is the water in contact with the reactants. And we're measuring how the temperature changes for the water. So in both cases, water is key. The main difference is that in bomb calorimetry, pressure increases, but volume stays the same. Whereas in coffee cup calorimetry, the pressure is constant. So this brings us to the idea of heat capacity, which we spoke a little bit about when we looked at the simulation. All right, so if I make soup and I leave a wooden spoon and a metal spoon in the soup and I walk away for a while, when I come back, I'm not inclined to grab the metal spoon because the metal spoon is going to be hot. And I know that. I know that because when I was like 2, I tried to touch some metal thing and it was hot. So we learned that from a really young age. We have an intrinsic understanding of the heat capacity of an object. So things that transfer heat really easily, like the metal, have low heat capacity. In other words, they don't have the capacity to absorb heat very well, so they're going to transfer it onto my hand really fast. Wood, on the other hand, is an insulator, just like bricks are, which means it has a high heat capacity. I looked this up once. It's somewhere around 5 joules per gram for every degree. And the heat capacity of most metals is way less than 1. So like, for example, iron is 0.48 joules per gram degree C. Okay, and so the idea here is that any 2 objects in contact with each other will transfer heat. If I put an ice cube into a cup of tea, the ice cube warms up, the cup of tea cools down, and they both end up at the same temperature in the end. Okay. These 2 objects feel at different temperatures because they transmit heat differently. That's the concept, heat capacity. So I want you to come up with a definition here. If you cite another source, then that's okay, but say so. Or you can use your own words based on our discussion here. That's probably better. But either way. The symbol that we often use for heat capacity is C. Some places, some different textbooks use S or SH. So there's no standard value here. And so you should be kind of accustomed to thinking about it in a lot of different ways. The formula could be Q equals MCAT or Q equals MSAT or MSH delta T, like that. So it comes in a couple of different ways. But it's the same quantity either way. And so heat capacity for water is one of the most important quantities in the world. We use it for so many different things. So it is defined as 4.184 joules for every gram degree C, or 1 calorie for every gram degree Celsius change. Okay, so this is a constant that depends on, this is liquid water, I should say. It depends on the state of matter and it depends on what the material is. All right. When we have 2 objects in contact with each other, their heat exchanges until they are, equal to each other. So what this means is the temperatures of 2 objects in contact will be the same. And the heats are the same, but they're opposite, right? So if I have a hot spoon and my hand, when I touch them, if I held on to it, eventually the hand and the spoon would have the same temperature because the spoon cools down and the hand warms up. And so when that happens, the heat from the spoon, the Q from the spoon, leaves. So Q that is exiting is negative. But it's going to be equal to the Q that my hand absorbed. Okay? So they're equal but opposite. Whereas temperatures are just exactly the same value because it's measuring heat transferring. Okay. So here's an example of a calorimetry problem. We are going to do a lab this next week about that. So this is a good thing to dive into. So if I have 10 grams of metal and I heat it from 20 to 100 degrees, so our change in temperature here is going to be final minus initial. So the final is 100 minus the initial, which is 20. And we got to remember sig figs when we subtract, so it's only going to be 80.0, even though there's 4 digits here. It doesn't matter because we only have the tenths place, so I can only keep the tenths place. So our change in temperature for the metal is 80 degrees. Then I put the metal into a coffee cup calorimeter and I fill it with 45 grams of water that's at 19.5. The water and the hot metal sit together, so the water heats up and the metal cools down. Okay, so the delta T of the water now is going to be the final minus the initial. So it went up by 5.2 degrees. The mass of the water is probably going to be important here because they gave it to us. I'm assuming I'm going to use it for something. And I know from the last slide that the heat capacity of water is 4.184 joules per gram degree C. So conveniently, we know an awful lot about water, which means I can find the heat for the water. So it's going to be mass times heat capacity times the change in the temperature, which is 5.2 degrees Celsius. So the heat capacity has those funky units because everything cancels except for energy. So joules is all that's left from this equation. Okay, so here we figure that the heat for the, oops, you can't see that. That's hard to read. There we go. The heat of the water is equal to mass times heat capacity times the change in temperature of the water. So here that equals, well, my calculator says 979.056, but I have 3 here. Oh, I only have 2 here. So I guess 979 joules is going to round to 980 joules for sig figs. Okay, so that's the heat change for the water. All right, well, so the heat of this reaction, so in other words, the metal cooling down, the heat of that reaction is going to be equal, but opposite. The metal got cold and the water got warm. So in order to figure out what the Q of the metal is, I just take Q of the water and I turn it negative, because they're equal but opposite. So in other words, the metal gave up 980 joules, the water absorbed 980 joules. Okay, so that's a calorimetry problem. And this leads us to add on to our equations, okay? If you are still having difficulty with balancing reactions, which is going to be part of Chapter 5 as well, and also going forward, this is a really cool simulation. So go back onto your notes, click on this simulation. It lets you build molecules and reactants and balance things, and there's excess reagents, so it's also a good way to practice limiting reagents if you'd like. And then here is your assignment. Do this problem as part of your homework, and you're going to turn it into me in class. If you have any questions about it, please feel free to send me an email. It's a good idea to answer question number 3 before you come to class because this material will be on the test.